Thank you for having me here. I really like one of the sentences that you said, Helena, which is that we are lacking reliable kinetic data. And that is kind of the summary of what I'm going to present. So this is a very good transition to this talk. So in more the talk I'm talking about, if you're an attendee of the users meeting, you will have already heard about our project DRI, and this talk is on our latest efforts in it, and a bit explaining to you why it's so complicated to do this. So there's this one number that every steel talk starts with, and it's the amount of CO2 that the steel industry accounts for, which is about 8%. The sources vary, and this is quite big, sometimes 7% is here. This is a big problem that we have to work on in order to fight climate change. And if you look at the processes of the steel industry and steel making, you first have the iron making process, then you have the steel making process, and finally the finishing. And a very, very large percentage of these CO2 emissions that we are trying to reduce is the iron making part. We are trying to get the iron ore and making this towards iron in order to have this as the ingredient for the steel making process. And there's two different routes that I'm showing here, the blast furnace route and the DRI route. And the DRI route is one of the routes that is really promising because there is the potential of reducing the CO2 emissions from the blast furnace route by 97%. If you reduce your iron, so in the DRI route you have pellets and they are porous, and you reduce them with CO in very traditional ways. You can, however, replace this with H2 and do hydrogen reduction. In pure hydrogen reduction, you could save up to 97% of the CO2 emissions of the blast furnace route. So this is why we are focusing on this, because it's a very promising candidate to decarbonize the steel industry. The problem is that the hydrogen direct reduction is a very, very complex process. And this is what all of this talk will be about. And in this DRI route, and if you have attended last year's user meeting, we tried to show that it's very difficult to model this. And modeling is very necessary because it's very expensive to do all these experimental trials to do the DRI and find out what is the most efficient H2 ratio. Do you use mixed gas atmospheres? What happens if you mix them? There's this big problem that CO reduction would be an exothermic process, H2 reduction is an endothermic process. So there's a lot of very complex processes in the direct reduction that would be very good if you had an accurate process model in order to understand this process better and then also to make it more efficient for steel companies, for example. And this accurate process modeling is what we are trying to do. And the big question that we always get if we talk to, for example, the steel industry is that they are interested in the metallization degree. Because if you can see here, there's the DRI, and then the next step would be the electric arc furnace. And it is really important what the metallization degree is of your DRI, so how much you have reduced your iron oxide to iron in order to then put it into the EAF. Because if you have a too low metallization degree, then the iron that is still in an oxide is lost in the EAF slag. But if you have a too high metallization degree, you also have an inefficient process. And what we're talking about here is not 60 or 40%. We are more in this range that Moritz already mentioned. So they're very interested if it's 94 or 97%, for example. So this requires very, very accurate process modeling in order to be able to distinguish 94 from 97. And this is what I want to ask in this talk today and try to answer. What do we need to consider in the model for predicting the difference between these 94, 97, or 93 and 98% of metallization degree? This is what you have already seen in Moritz's talk. And this is our understanding of how you have the different levels in a or abstraction levels in a process model, and all the levels that you would need to accurately model a process. And there is, of course, a lot of complexity to this DRI process. And if we try to consider all of them, we can have a look at the direct reduction. And here, it's again, you see the pellet, and then you have multiple pellets in a furnace. They go from the top to the bottom, and you have the reduction gas going from the bottom to the top. And they're reducing it. We are for now only focusing on the pellet scale because there's a lot of pellet scale phenomena that are very, very important, not only for this pellet scale, but also for the macro scale. And in order to have a reliable process model, you already need to be able to accurately model the pellet scale, because reduction kinetics are highly influenced by the pellets, the gas utilization in the furnace, your metallization rate, of course, and that's what we're talking about, the heat balance, or also the productivity. And on the pellet scale, it's not only just one sphere and you're trying to reduce it. It's quite a complex, already the pellet itself is quite complex in its structure. So you have this conversion curve, that is the bottom left plot, where you have the reduction of Fe2O3 with mass loss then to Fe. So conversion curve value of 0 would correspond to 0 conversion, so Fe2O3, and then you have a value of 1 if you have converted it fully to iron, so a metallization degree of 100%. But these pellets have a very complex structure, these tortuous pore networks, and there's this nice video that Mo has already announced, and I hope this works now. Yes. Because you have some pores, and if you then zoom out, you have a different pore structure and pores on a different length scale, and then more pores on a very different length scale, and bigger pores, and it's very, very, very complex to understand this and model all of this. And there is a lot of pellet models already. So you could ask a question, and this would be a very fair question, why would we need another one? There's very famous ones, there's cold shell models, there's grain models, there's the porous solid models, and all of them are widely used in literature. And my talk last year at the users meeting was exactly about this, why these models all have some problems, and the plot summarizing these problems is this one. Finnish group, and they published a review article. They looked at all of these pellet models, and then they took the values that these pellet models published about the activation energy of the 3 different reduction steps from Fe2O3 to Fe3O4 to FeO to Fe. And they plotted this activation energy nicely here, and all of them vary in the range that the actual value is in. So somehow, either one of these models is correct and all the others are incorrect, or all of them are a bit incorrect. The question is which one is correct. And this is also why we have been trying to figure this out. So how can we make these models more accurate, and how can we create a model that considers all of these very different complex processes in order to maybe have a more reliable model that can accurately determine the kinetics of this process. The most famous model is the core shell models. It looks like this. So it's a pellet, and it has distinct regions where one phase is present. So you have the core that is unreacted Fe2O3. Then around this you have a region with Fe3O4, FeO, and Fe. And then these reaction zones move over the course of the reduction. And the problem with this model is if you compare it to experimental data, this is one of the papers I like the most. It's from Jan Ma from the Max Planck Institute for Sustainable Metallurgy. And what they did is they reduced a pellet, or they took a pellet, they reduced it for 30 minutes, and then they looked at the cross-section, and then they looked at different locations in the pellet and checked what phases are present. And this is plotted on the left side, on the right side. And if you see, there's multiple phases present at the same time. So we have in the pellet surface a bit more alpha iron, but also magnetite and wüstite. In the pellet core, in the bottom, we have a bit more magnetite, and then also wüstite and alpha iron. If I plot this now, you have the pellet radius on the x-axis, and you have the phase composition on the y-axis, then it would look somehow like this. I only have 3 points, it's quite difficult to plot, but this is how it would look like. If I would try to represent this in a core shell model, it would more look like this. There can only be one phase present at the same point in the location, and this does not really represent the actual structure that I observe in experiments. So this is one of the explanations why these models all vary in the kinetic parameters. If you look again at this nice gray boxes that Moritz already established, they are considering phases, but they're definitely not considering phase assemblage. They don't have 2 phases present at the same time. And you can do this for all of the other models. And if you're interested, you can watch the YouTube video of my talk last year. But based on all of this work, we have tried to come up with our own model, the GTT porous solid model that is based on the work of Frade et al. From the DLR. And we have tried to extend this porous solid model. And what we have been doing is that you take the pellet and assume it's a porous solid, and then you have a gas flowing through this porous solid. A gas stream that can have different compositions, it can have H2 and CO in different mixtures. And then you reduce your Fe2O3 to over these 3 stages to alpha iron. You just apply the energy of mass conservation to it, and discretize this equation in space. So at every point and location, here at the core of the pellet, you have a certain gas composition, a certain pellet composition, and a certain porosity. And then you also have this, if you move out in the radius, and then you discretize it at these different locations, and you don't only do this in space, but also in time. And with this, you can solve this energy of mass conservation. We also take into account the driving force, which is also something that Moritz pointed out is quite important. And with this, we have tried to come up with this porous solid model. What this model can do is that it is able to predict the microstructure because more phases can be present at the same time, because we have this phase composition inside the mass conservation equation. We have made it thermodynamically consistent, which was one of the problems with the porous solid model as proposed by Frade et al. By taking ChemApp into this model and making it evaluate the driving force. And what was most important to us was that we have drastically reduced the amount of fitting parameters, because this was one of the big problems, that you always need experimental data to validate your model in some way. And if you have too many fitting parameters, it's quite easy to fit the experimental data. If it's physically sound, it's not really a question then. If you're interested in all of this, you can read our article that we published. You can scan this QR code. But today I would like to talk about something else, because we are quite proud about this paper. And if we go back to this structure, then it kind of, we are not at the process scale yet, because we haven't upscaled it, but we are still at the pellet scale. But we have some kind of microstructure and phase assemblage, and we have also some phases in there. But there are some big construction sites that we are working on. And why this is so complex, and why we're still working on this, and why this is also important, and we would like to communicate this to the scientific community, that it's very important to also consider these effects, is what I'm going to show you today. Let's start with the microstructure. Most pellets, or pellet models, and I would even dare to say almost all pellet models, use the Langmuir-Hinshelwood kinetics, which means that you have this reaction rate, and it depends on the composition of the gas, of the solid, the kinetic parameters, and the equilibrium constant. And then it looks somehow like this. The green curve is the conversion degree. So you go again from 0, which would be Fe2O3, to 1, which would be alpha iron. And if you plot the reaction rate, which is the right axis, it's in red, you would just have a linearly decreasing reaction rate, because you first form, it first goes fast, and then it goes always slower. And this is the very easy and first approach to these kinetics. The problem is that we are all probably metallurgists, or most of us, and what we learned in university about how this works is that first grains have to nucleate and then they have to grow. But this approach does not consider any of these nucleation and growth phenomena. And this is a big problem, because if you would look at the same curves with nucleation and growth, then it would look somehow like this. So you would have some kind of incubation time, because you first need to form the nuclei, and then they can grow. That's also why the blue curve has this dip in the beginning. And that also means that the reaction rate is not linearly decreasing. It is first increasing a lot, because you form nuclei. And it's something we're going to implement in our model at the moment. This is what we're doing on the theoretical level. But of course, what we need for this is somehow experimental data in order to corroborate what we're doing in the model. And this is quite difficult because experimental data is not always available. And that's why we are so thankful that we have Ömer, who is also not only working with us, but also doing his PhD at the Max Planck Institute. And he's doing a lot of experiments. And we designed these experiments specifically in order to make it possible for us to use them in our model. And how they look is like this, of course. We're GTT, so we start with a phase diagram. This phase diagram plots the temperature over the H2 to H2 plus H2O ratio. And we are trying to look at how the phases nucleate, but for that we have to have them nucleate one after the other. And that's why we select conditions for our pellet reduction experiments, where we select these H2 to H2O ratio so that we are in a thermodynamic region where it's only possible, for example, to first form Fe3O4. And what you see is this corresponds to this blue conversion curve. It doesn't go up to 1. It goes up to approximately 1/9, because if you convert Fe2O3 to Fe3O4, approximately 1/9 of your oxygen atoms go away, and that's where it converts. You can also see that it approaches this, and then it stops there because it cannot go any further, because it's not thermodynamically stable to form, for example, wüstite. So we can look at this conversion, and then we can, when we have fully converged to Fe3O4, we can do a next step. So we move our conditions to be in a ratio where it is possible to form wüstite again, and now we move from Fe3O4 to FeO. Again, we converge exactly at the value that corresponds to the mass loss that you would have for 100% wüstite. And then the same thing we can do for iron. Of course, these processes become slower. And if we look at them, for example, at the first step, we can look at these convergence degrees and we can stop them at any time. And this is also what we are doing. Take out the pellet and look at the cross-section and look at which phases are stable at which point in time, which is an output of our model. So we can use this as experimental input for our model in order to confirm which phases evolve in which way and how to model the kinetics. And if we do this, we get these nice, colorful images. The left one is cool, and the green one is the interesting one. So we have taken a pellet out that was reduced from Fe2O3 to Fe3O4. It could only be reduced to this. And we took this point here and stopped the reduction at 100% Fe3O4. And then at different points in the location, so at the bottom is the core of the pellet, the top is the surface, and the middle region is something in between. We looked at how the grains actually grow. And in the green plots, you can already see, okay, there's a difference in porosity. We have more bigger pores at the core of the pellet. We have more smaller grains at the surface of the pellet, which is also the region that first gets reduced because it's first in contact with the gas. And we can not only do this for 100% conversion, we can also do this, for example, for 50% conversion. And there it becomes interesting. Again, please look at the green and red plots. Because here we see a distinct difference between the core and the surface. At the surface, we can start in core. At the core, we have mainly still Fe2O3. We have very big grains, and we have some nucleation sites of Fe3O4. The nucleation happens at the pores, which makes a lot of sense because that's where the gas goes through. And then if we go towards the surface, we have more of these green grains, and at the surface, we're already more reduced. We can look at how these grow, we can look at where these grow, and we can try to take this into account. For example, by plotting this, that you see on the right side, and this is now included in our model, so that we have the grain size distribution, and we see, so the left side, the 100% conversion, is these curves, the one that are not dashed, and we have the dashed ones, which are the in-between ones. You can see that the green one, for example, first nucleates here and has smaller grains, and then the grains grow, so it moves to the right. And we can learn a lot about our pellets and do this as an inclusion in our model in order to consider this. But as you see, this is a very complex process, and we would need to do this for every single step in order to understand how this actually works. Okay, this was the microstructure. I told you there's a second thing that we are currently dealing with, and that's phases. I already told you that we are doing pellet experiments, but what we do is we ask the Institute of Eisenhüttenkunde here in Aachen to produce pellets for us that are pure Fe2O3. which is very nice because we can just reduce them. However, these are actual pellets. Actual pellets that you buy from commercial suppliers are not only Fe2 or 3. They contain a lot of impurity elements. Some because the mines already have some impurities, some because, for example, you need binders in order to make the pellets stick together, which is some of the problems that we have with the pure Fe2 or 3 pellets. And all of them affect the reduction degree, and also they affect the metallization rate, of course, because we are in a very small margin of where we would like to evaluate how much it reacts and how much the metallization degree is in the end. However, if I would try to model this, this is very, very complex because they do not all interact already with each other and interact with the kinetics. They also interact with iron, and they all influence each other. So it's very, very difficult for us to model the influences of all of these different components if we have all of them together. That's why we are very happy for our colleagues at the University of Duisburg-Essen, because they help us to create pellets that only contain, for example, SiO2. So then we can study the influence of what does SiO2 do to the reduction degree, and then we can go to other elements. If we start with SiO2, we have here a pellet with pure hydrogen reduction. It has some iron oxide and SiO2. And this plot you have already seen today. If I calculate it with FactSage, this is what comes out. For different H2 to H2 plus H2O ratios, I get different phases that are stable. Of course, the left side corresponds to a higher oxygen partial pressure, the right side to a lower one. So in the left side, I get Fe3O4 stable, and then I get to FeO. And alpha iron, so pure iron, which I need for 100% metallization degree, is only possible in the right side of this plot. So I need at least about 67% in this ratio in order to manage to get iron in the first place, which is relevant for all the metallurgists that are running these processes and have to somehow adjust the ratio of H2 to H2O in their furnaces. But when I look at this, then the 100% conversion with respect to iron is only reachable in this red shaded region, because before that there is also iron in Fe2 SiO4. And I need a very, very high H2 to H2 plus H2O ratio in order to get this, reduce this Fe out of this phase and then have it in the alpha iron, and then have SiO2 as well. So this is the metallization degree of 0.87 that I can at maximum reach if I do not go to these very, very high regions. And this is quite important because this is the real value of how much water vapor I can have in my furnace. Again, this depends on the oxygen partial pressure, which is plotted here. So it's somehow the logarithm of the oxygen partial pressure is somehow minus 21.4 for when I reach full conversion of iron. Okay, now it becomes more complex. I want to add a new element, a new molecule. So let's go to SiO2 plus CaO. Of course, as GTT, we start with a phase diagram. So on the left side of this phase diagram, you have pure SiO2. On the right side, you have pure CaO, and then the mixture in between. So with the first part that I just showed you, we would be on the left side. And again, here you see this value of minus 21.4, which is exactly the region where we can reach 100% iron. Above this, iron is in Fe2 SiO4, and we cannot have full metallization. But if we look at this now, and go further to the right in this diagram, then actually the full 100% conversion of iron moves up. It moves up to minus 20.1 if I add more CaO. And if I look at the plots with the oxygen partial pressure, this also means that the region of how much H2O vapor I can have in my furnace moves to the left. So I have a much bigger process window for my furnace in order to operate to actually reach the 100% conversion. Again, without this, I could only reach 87%. That's not enough for most of the processes. So it's quite relevant where I am in this phase diagram and what this ratio of SiO2 to CaO is. Of course, I could play this game more, and we could add a third element or a third molecule. So this would be fun, but we are not there yet. the only message I have is that this is a very complex process, and we're working on having all of these different stages in our model, but it's quite complex, and we're trying. And we are trying to also generate the experimental data in order to validate it. I hope that you are now all fans of direct reduction and that this is an exciting topic, and thank you very much for your attention.